In this video, I want to talk about both the linearity and the existence of the Laplace transform. I'm going to start with linearity. The first piece of linearity says if I want to take the Laplace transform of a sum of functions, I can take the Laplace transform of each piece and then add it. So I can break up a transform over addition. And the second piece says that the Laplace transform of c times f of t is c times the Laplace transform of f of t, so I can multiply by scalars as well. The second piece said that the transform of c times f of t is c times the transform of f of t, so I can move multiple constants in and out. Let's do an example of using this. I want to find the transform of 11 plus 5 e to the 4t minus 6 sine 2t. In my last video, I had done all three of these transforms, both defined them and derived. And this is what I'm going to use. Using linearity, this one here will be 11 times the transform of 1 plus 5 times the transform of e to the 4t minus 6 times the transform of sine 2t. Using what I have, the transform of 1 is 1 over s. For e to the 4t, I'm going to let alpha be equal to 4, so this will be 1 over s minus 4. And for sine of 2t, I'm going to let b be 2. So this will be 2 over s squared plus 4. We can then simplify. This will be 11 over s plus 5 over s minus 4 minus 12 over s squared plus 4. So we have our transformation. The next thing I want to look at is, when does this transform actually exist? Does the Laplace transform always exist, or are there conditions? For the Laplace transform to exist, the integral from 0 to infinity of f of t must converge. And there are two requirements for convergence. The first condition we need is f of t must be piecewise continuous. So let me look at what that means. Here I have a function that's piecewise continuous. While it is a discontinuous function, I do have jumps. Each piece is essentially continuous. The actual thing that we need is all of my right hand and left hand limits must exist. They don't have to be equal. So for instance, the left hand limit as x goes to 1 is 1, the right hand limit is 2, but they both exist. So this would be piecewise continuous. On the other hand, this graph here would not be piecewise continuous. This one would not work, in particular because the right hand limit as x goes to 0 does not exist. So not all of my right hand and left hand limits exist here. Therefore, this is not piecewise continuous and would not have a Laplace transform. The second thing we need is that my function f of t must be of exponential order. So what do we mean by that? What we mean is that if we look at the absolute value of f of t, it should be less than or equal to m times e to the alpha t for some finite numbers m and alpha. So essentially I need to be able to bound it by an exponential. Let's look at some examples of this and determining if things are of exponential order. So we'll consider f of t equal to e to the t squared. In reality, what we want for exponential order is I want to be able to look at the limit as t goes to infinity of my function f over e to the alpha t to be finite. So let's see what we have here. This will be the limit as t goes to infinity. Using properties of exponents, we can write this as t squared plus alpha t. As the limit as t goes to infinity of this, the exponent would tend to infinity, and e to a really big number is a really big number. So this would be infinite. So this tells me this is not of exponential order. I did not get my limit to be finite. Now let's look at this one. It seems like it would be of exponential order since it is an e to the 5t. But let's do it the same way we did the last example. The limit is t goes to infinity of my function over a generic e to the alpha t. This will be the limit as t goes to infinity of e to the 5 minus alpha t. So this limit has two pieces. So if 5 minus alpha is positive, greater than 0, or 5 is greater than alpha, then this exponent here will be positive, and e to a really big positive number is a really big number. So this would be bad. This would diverge or be infinite. However, if 5 minus alpha is less than 0, so in other words, alpha is bigger than 5, then this exponent here will be a really big negative number, and e to a really big negative number is 0. So this works provided alpha is greater than 5. So in other words, the absolute value of f of t is bounded by something like e to the 6t. This is not the only possibility here. It works for any number there greater than 5, but this is one example.